In this video, we'll see some examples. Okay, so the last part of this fifth section of our chapter, our determinant chapter, is going to be about some examples. Okay, examples. So in these examples, we will apply all the concepts we have seen in the previous video. We will see how to find the area, the orientation of a box formed by vectors, the volume, okay, and find the size of a transformation. And yeah, also we are going to apply the concept of the product of the determinant of two products, which is equal to the product of determinants. Okay, so let's start with the first question. We have consider the following vectors. Okay, v1, which is equal to minus 1, 3, and v2, which is equal to minus 1, 4. And part A, we are being asked to find the size of the box defined by these two vectors. Then in part B, we are being asked to find the orientation. Okay, and in part C, we are being asked to find the volume. Okay, let me split this into two so that we can have enough space. Okay, let's start with part A. Okay, we have seen earlier, okay, that determinant the size of the box is going to be determinant of these two vectors, minus 1, 4. Okay, so here we don't need to do the Gauss's method. We can just apply the formula of determinant. So determinant of the box is minus 1 times 4 minus 3 times minus 1, which is equal to minus 4 plus 3, which is equal to minus 1. So the size of the box is equal to minus 1. So based on that answer, we can get the orientation. We have seen in the previous video that the orientation is determined by the sign of the size function. So if it is the sign is negative, then we have a clockwise orientation, but if the sign is positive, then we have counterclockwise orientation. Okay, so the orientation is clockwise. So that means we are going from vector, so that means we are going this way. Okay, vector, the first vector, second vector. Okay, v1, let's call this v1, v2, and let's assume v1 is minus 1, 3, and v2 is minus 1, 4. So we are going clockwise. That's why the size function is negative. Okay, part C, we are asked to find the volume. So the volume is going to be, as we have seen earlier in the definition, is going to be the absolute value of the size function. Okay? So absolute value of the size of the box, which is the absolute value of -1, which is equal to 1. So that's the volume. Okay. So that's it for this first question. Let's do, oh sorry, that's the end for the first example. Let's continue with another example. Okay, it says the following: by what factor okay, by what factor, okay, does the following transformation change the size of the boxes? Okay, so also in the previous video, by what factor? That factor is going to be the size of the matrix representing this transformation. So the transformation is defined as T from R2 to R2, such that for xy we have 3x minus y minus 2x plus y. Okay. So to be able to find that factor, what we need to do is just, first of all, we need to find the matrix representing this transformation, and then we need to get the determinant of that matrix. Okay. So step 1, find T, the matrix representing. Okay, maybe I could split this into two. Representation of T with respect to the standard basis. Okay. So from the previous chapter, we know how to represent a matrix. So first of all, what we need to do is to see where does this transformation send the basis vectors to. So the basis vector, the standard basis, the basis B is equal to 1, 0, the standard basis of R2, 0, 1. Okay, so let's see where this transformation send these vectors to. So 1, 0 is being sent to, say, 3 times x, okay, which is 1, minus y, which is 0. And here minus 2 times x, which is 1, plus y, which is 0. So this is equal to 3 minus 2. So, okay, so That means 0, 1 is being sent, okay, to um, 3 times is x minus y, my y is 1, and minus 2 times 0, okay, plus 1, which is equal to minus 1, 1. Okay, and so what is good with standard basis is the fact that the representation, okay, representation of the vector 3 minus 2 with respect to b, okay, the codomain basis. So what we have to notice here is the domain and the codomain have the same basis, okay, they have the same basis, which is p. So we need to represent these vectors, the images of 0, 1, 1, 0 and 0, 1 with respect to the basis of the codomain, which is also p. And what is good with standard basis is the representation of a vector in standard basis is the same as that vector. So it's going to be 3 minus 2, and also the representation and the representation. So I'm sure you know how to get the representation of a transformation. We have done plenty of these examples, okay, from the previous chapter. So if you don't recall how to find the representation of a transformation, just look back to our previous chapter, okay. And the representation of minus 1, 1 is equal to minus 1, 1. So the matrix representation of T, so the representation of B, of T with respect to B is going to be equal to 3 minus 2 minus 1, 1. Okay, so this is our matrix T. Now, step 2, to be able to find the factor we are looking for, step 2, find determinant of T. So, determinant of T is equal to determinant of 3 minus 2 minus 1, 1, which is equal to 3 by 1 minus 2 times minus 1. I'm sure you remember how to find the determinant, okay, of 2 by 2 matrix without necessarily using Gauss's method or Laplace expansion or Laplace formula. We already have we have a formula for 2 by 2 matrix, okay, determinant of 2 by 2 matrix A, B, C, D, then determinant, so let's say A is equal to that, so determinant is equal to AD minus BC, okay. So here you have 3 minus 2, which is equal to 1. So this transformation is going to multiply the boxes by 1. That means it leaves the boxes unchanged, okay. So that will be all for today, okay. So here, let me just say transformation T, this is what we have. So in these two examples, we have seen determinant as a side function, how to use determinant or how to define determinant as a side function, and how to use that that side function to get the orientation of the box formed by the vectors, okay, and also how to find the volume. And we can also find the factor by which the original box is multiplied to under a transformation, okay, by using the method I have just showed you here, which is simply to find the determinant of the matrix representing that transformation. Okay, I think we can stop here for today. Thank you and see you in the next video. In the last part of this chapter, we will talk about the application of determinant, okay, and as we'll use determinants as a mean to find the solution for um, linear systems of equations. So basically, in the next video, we'll talk about Cramer's rule. Thank you and see you.